Hey guys, so today I'm just going to be working out some practice problems for chapter 11 from Solomon's. These are just practice problems that I pulled from our class resources, and this week you'll just be able to see me writing out by hand what's going on. So for practice problems like this that are in the condensed formula, I always move them over into the bond line formula because that's just so much easier for me to see. And from there I do 3 steps. 1, find the parent. 2, name substituents, and 3, combine everything alphabetically. So first, the parent chain is going to be the longest carbon chain, and you want to start with numbering it where the highest priority substituent has the lowest number, or where if they're all the same, where those substituents have the lowest numbers possible. So in this case, alcohol is the highest priority, so we'll start from this side. And so we number 1, 2, 3, 4, 5, and 6. So the parent chain is hexane. Okay, and then we're going to look for the substituents. So there's a 2-ol, that's a suffix, but alcohol on the second carbon. And there's a methyl group on carbon 3, 4, and 5. 3, 4, 5, and that's trimethyl. So if you're going to combine that all, it would be 3, 4, 5. Oh, my dash got a little weird. Trimethyl hexane dash 2-ol. Alternatively, you could do 3, 4, 5, trimethyl 2-hexanol. This is a little bit more specific. It puts the 2 right before the suffix, but either one of these is technically correct, so that means your right answer here would be answer choice D. Okay, and then I go through the same method on question 2. So for question 2, we're going to find the parent chain. So there's 3 carbons, so 1, 2, 3. So that would be propane for step 1. For step 2, our substituents are going to just be these alcohols, and they'll be on carbon 1 and carbon 2-ol. And when there's 2-ols, it's diol. So then if we combine it, that'd be 1, 2 propane diol, or you could say propane 1, 2 diol, and either one of those should be correct. So then your right answer choice for this one should be answer choice D again, 1, 2 propane diol. Okay, and so the next one is select the structure of benzyl methyl ether. Okay, benzyl methyl ether. So in this case, ether is going to be your oxygen, and on one side you're going to have a methyl group, and on the other side you're going to have a benzyl group. Okay, and so benzyl groups, you might just be thinking it's a benzene ring, but actually benzyl has a CH2 before it. So the way I remember this is benzyl has a bend in it. So if you just have a direct attachment, so if you had this, that would actually be a phenyl methyl ether. But see how there's a bend right here between the benzene ring and the oxygen? That is benzyl methyl ether. So you're looking for this structure. That is benzyl methyl ether. And it looks like, so this right here, that would be your phenyl methyl ether. So this answer choice C must be the right answer for benzyl methyl ether. Okay, and then moving on to number 4, which compound would have the highest boiling point? Okay, so this goes back all the way to your Gen Chem knowledge. Highest boiling point is going to have the highest intermolecular forces. So the strongest intermolecular forces and the most of them. And the strongest intermolecular force is hydrogen bonding. And I know that seems like a bond. I spelled hydrogen wrong. Hydrogen bonding, and I know that seems like a bond, but it's actually an intermolecular force, so it's between 2 molecules. And once those separate, if the attractions that are getting two molecules closer together, the weaker those are, the more easy it is to spread them apart into a gas, which has very little contact with other gas molecules. So we're looking for something that has the most possible intermolecular forces, so a hydrogen available for hydrogen bonding. And so there's no hydrogens available for intermolecular forces here. This is just going to be London dispersion forces. Here we have an oxygen, but that's not going to be available for hydrogen bonding because there's no other hydrogens available. So remember, hydrogen bonding is a hydrogen bonded to fluorine, oxygen, or nitrogen. That's when that hydrogen is available for hydrogen bonding. My chemistry teacher called this H with fun on it. So this is just going to have dipole-dipole interactions for intermolecular forces. This has an alcohol with a hydrogen on it. So this could partake with other molecules in hydrogen bonding right here. So that is an option. When we go down here, this one also would partake in hydrogen bonding. But all the way at the bottom, you have two alcohol groups, and that makes this the best candidate because it has the most hydrogens available for hydrogen bonding. So the forces between this, say if you had another one of these are going to be able to strongly connect to each other. This hydrogen is going to come over here to this oxygen and form a nice, strong intermolecular force between the two. Okay. I'm going to move on to question 5. I'm a little worried my pen isn't dark enough, so I'm actually just going to switch to a black pen. It's maybe a little bit easier to see. Yeah, okay. So number 5, which alcohol would undergo acid-catalyzed dehydration most rapidly? So let's go over acid-catalyzed dehydration. So if you have an alcohol group, and it's in the presence of, sorry, my hand's blocking it there, a proton, this would come and attack, and you'd end up with OH2 plus. So once you have that water, basically, H2O, it's got a positive charge on it, but it's going to be water as soon as it leaves. So once you have that, the leaving group can leave more easily, leaving a carbocation. Nope, I did not mean to draw that there. So we would have something that looks like this. Then, if you have a base in situ or whatever you've got going on, maybe the acid that lost this, it can attack this proton, leaving these electrons behind to fill in this gap, and you get the formation of an alkene. So which alcohol would undergo acid-catalyzed dehydration most rapidly? Well, the slowest step, the rate-determining step, is this leaving group leaving and forming a carbocation, because that's not very stable. So the one that will have the most stable carbocation is going to be the best option. So I would draw all these out and look to see which is going to give you a tertiary carbocation. So 3,3-dimethyl-1-butanol, so butane is 1, 2, 3, 4. If it has an oxygen on 1, alcohol on 1, and then that's carbon 1, 2, 3, has 2 methyl groups, then that's going to give you a primary carbocation. That does not happen very well, so that's probably not going to be your option. 2,2-dimethyl-1-butanol, so it's the same basic structure, but it's moved over 1, so you'd end up with this, and that could undergo rearrangement, so that would be a better option, but still not a great option. 3,3-dimethyl-2-butanol, so 1, 2, 3, 4. Now our alcohol is secondary, so that's better, and then we have rearrangement as well. So this would probably undergo dehydration, especially with the rearrangement, but the very, very best one is going to be this 2-methyl-2-butanol over here, because that is going to be 1, 2, 3, 4, 1, 2-methyl, 2 alcohol. So when the leaving group leaves, it will be a tertiary carbocation. It'd be even better if you have another methyl group there, but we don't right now. So, okay, so the right answer would actually be answer choice D. Okay, and then next we're going to go over question 6. Which products would you expect to obtain from the following sequence of reactions. So this is hydroboration oxidation. So this is addition of an alcohol. You're going to get syn addition, so they'll add to the same side. But they're going to add anti-Markovnikov. So normally when you have regular old addition of, actually let me grab a separate sheet of paper. I don't have a ton of space here. Okay, so normally when you get the addition of alcohol on one side and hydrogen on the other, or also that's called addition of an alcohol or addition of water across a double bond. Say you have a double bond that looks like this. Actually, that's not a good one. We'll start with this. Something that looks like that. So if you have acid catalyzed addition, first your double bond's going to attack, and you'll end up with the hydrogen will add on this side, and you'll get a carbocation on this side because you've lost a bond here. So there's a positive charge remaining. And then alcohol will come and attack, or a hydroxide ion will come and attack on the other side. And this is known as Markovnikov. I just call it Mark. Now you can do hydroboration oxidation to get anti-Markovnikov, where it's going to add to the opposite side, the less substituted side. So Markovnikov adds to the more substituted. Anti-Markovnikov would add to the opposite side. So your hydrogen would add on this side, the more substituted, and the alcohol would add to the less substituted side. Anti-Markovnikov. So in this case, there's no stereochemistry to account for because they're all going to have mirror images possible. But if we were, these would either have to be both wedges or both dashes because they go through that box mechanism. I'm not going to take the time to explain it right now, but you can go look it up in your textbook. So that's what we have here, hydroboration oxidation. So we're going to add an alcohol to the less substituted side, and we're going to add a hydrogen to the other side, and that double bond would go away. So we'd end up with a structure that looks like this. CH3, H, and OH. But it's also asking about stereochemistry. So our H and our OH both need to be either wedges or dashes. It doesn't matter, they can add to either side, but they're going to add to the same side. And the CH3 will be the opposite. So that means that if the OH is a dash or a wedge, the CH3 has to be the opposite. So the right answer here is actually answer choice C. Now what you might do on this, and they have this answer choice B in here to trick you, is that you might think, oh, they add syn, so they're both going to be wedges or they're both going to be dashes, so this is the right answer. But it's showing you the substituent that was already there, the CH3, instead of the hydrogen. So that's where some students go wrong on that question. Okay, so for the next question, which would be the best way to carry out the following synthesis? Okay, we have a few options here. Let's see, we're going from, I'm going to draw this out. 1, 2, 3, 4. See, I still number my carbons even after all this time. And carbon 3 has a bromine on it, and we're going from that to this. So when I look at this, there's no quick way to turn this bromine into an alcohol and move it one carbon over. Oh yeah, this is actually, should look like this, sorry. Because it's moved one carbon over. We didn't lose any carbons. There's 1, 2, 3, 4, 1, 2, 3, 4. So there's no quick and easy way to do this. So what I would suggest is that we would do some kind of an elimination, like an elimination reaction that you learned back in chapter 5 or 6, to get a double bond here and then add an alcohol. But that requires you knowing how to get your double bond to go here rather than here, and to get your alcohol to get your intermediate that would look like this, so that we can add your alcohol here, which requires anti-Markovnikov addition. So we just saw how to do anti-Markovnikov addition up here with hydroboration oxidation. So that would be your last step. You know for a fact that you're going to want to add anti-Markovnikov because this is a less substituted carbon and that's where the alcohol is. So then you can eliminate anything that adds your alcohol not by anti-Markovnikov method. So this is acid catalyzed, so that would be a carbocation, and same thing here, acid catalyzed, carbocation, and same thing here, acid catalyzed, carbocation. Those would all add Markovnikov style. So then we've narrowed it down to just 2 options, and both of these start, it looks like, with an elimination. But we don't want to get an elimination where the double bond forms here between carbon 2 and 3. We want it between carbon 3 and 4. So that